Thermodynamics is the study of heat transfer and its relationship to doing work. Since heat is energy in transit, it can be used to do work. It can also be converted into other forms of energy. Remember that the ideal gas law describes the properties of a gas. When we take all of those variables into account, it really ends up describing the energy of a gas. We represent that total energy of a gas as U. If we change one of those variables, we will also end up changing the total energy of the system. There are a lot of ways we could change the energy of the system. If we change one of those variables and keep everything else constant, that will cause a change in the total energy. We could increase the pressure, we could decrease the volume. Both of those are going to change the energy of our system. What would happen if we increase the temperature? We must be adding heat to it. The final energy must be larger than the initial energy if we add heat to it. So the change in energy must be the heat gained by the system. So say we have some system with some initial amount of energy. If we add some amount of heat to that system, the temperature will increase. Increasing the temperature can cause a couple of things to happen. In this case, we have a sealed container that keeps the volume constant. This in turn will cause an increase in pressure. If we look at what we have at the end, we see that the final energy is equal to the initial energy plus the heat energy that we added in. So if Q is positive, the system gains heat. If Q is negative, the system loses heat. Another consequence of changing the temperature of a gas is that we could have a change in volume. So say we have a piston. This is basically a container that contains a fluid and has a cap that can move up and down. Nothing can escape from this container, but any changes made affect the position of the piston. If we start our piston at a certain position, there is a certain amount of energy associated with the gas inside. This is the initial energy of the system. If the gas pushes the lid of the piston up, then the gas has done work on the piston. We know this because the piston has changed its height within the cylinder. And we know that if we change the height of a mass, then the work must have been done on that mass. So now we have a final energy associated with that gas. That final energy is the amount of initial energy minus the work that was done by the gas. A positive work means the system does work. A negative work means the system has work done on it. So if a system does work, the total energy of the system decreases. This brings us to the first law of thermodynamics. It states that the change in internal energy of a system equals the net heat transfer into the system minus the work done by the system. We are looking at how heat transfer is converted into work. This means that the conservation of energy is an important concept that can be applied to systems where heat transfer and doing work are the methods of transferring energy into and out of the system. To sum up this idea in equation, we use delta U as the change in total energy of the system. Q is the net heat transferred into the system, or out of the system. And we subtract the work, which is the net work done on or by the system. So the energy change of a system is equal to the total amount of heat energy that flowed into the system minus the total amount of work done by the system. Q and W are what we call path dependent, because they do depend on how they get into the system. They depend on what the gas is actually doing at that point in time. The change in energy is path independent because it does not matter how the change in energy actually occurs. At its simplest, the first law relates heat transfer, work done, and the change in internal energy of a system. If more heat is transferred into the system, then Q is positive, and there is a net heat transfer into the system. So a positive Q adds heat energy to the system. If the net work is positive, then energy is taken out of the system. If more heat transferred into the system than work done, the difference is stored as internal energy. Suppose there is a heat transfer of 40 joules to a system. Well, the system does 10 joules of work. Later there is a heat transfer of 25 joules out of the system, while 4 joules of work is done on the system. What is the change in the internal energy of the system? So we are looking for the total change in energy of our system. In order to find this, we need to know the total change in heat energy and the total net work done by the system. The total heat transfer can be found by taking 40 joules of heat. The total heat transfer can be found by taking the 40 joules of heat being added to our system and subtracting the 25 joules of heat leaving our system. This gives us a change in heat energy of plus 15 joules. The net work done by the system is the amount of work done by the system. The net work done by the system is the amount of work done by the system, which was 10 joules, minus the amount of work done on the system, which was 4 joules. So the total work done by the system is 6 joules. Our total change in energy is the amount of heat transferred into the system minus the amount of work done by the system. So from here we take our net heat change and subtract our net work to give us 9 joules of energy change. We could set this problem up another way as well. We are looking at an overall change in energy, so we can assume that every step of the process has a certain change in energy, and that each one of those energies contributes to the total. We know that in the first step we have a heat transfer of 40 joules and 10 joules of work done by the system. So the change in energy in the first step is 30 joules. The second step shows a heat transfer out of the system of 25 joules and 4 joules of work done by the system. Since heat transfers out of the system, we have a negative 25 joules of energy lost, and since work is done by the system, we have a negative 4 joules of work done. So the total change in energy is a negative 21.00 joules. The total energy for these two steps is 9 joules, the same as what we found in the previous setup. So no matter whether you look at the overall process or break it into its parts, the energy change will be the same. We talked about the change in energy being path independent because no matter how we look at the change in heat energy and the change in work, the total energy change is the same.